right, so here is our last of kind of this little series of introducing motion and using velocity or position time graphs. In the last particular video, we talked about the fact that with position time graphs, you can kind of see where something is at different periods of time. And that you can also use position time graphs to give yourself some sort of information about an object's movement. So, for example, if this is a position and this is time over here, if you have a graph of something that's going horizontally, that means it's staying at the same position over time. In other words, it's not moving. You also know that if something is going like this direction, it is moving. It's moving in the forward direction. It's moving to more positive distances over a period of time. And we also recognize that if you have a different slope like that if you're talking about the same period of time, like we say, taking a look at this particular spot right here, kind of going up this way. I'm just talking about one particular time. If we're talking about this time right here, this particular one, number 2 versus number 1, number 2 did not go as far as number 1 did in the same amount of time. Different ways to look at this. So this particular first line that's up here, line number 1, went, 5 meters in this many seconds, whereas number 2 only went, 2 meters in the same amount of time. We know that when we take a look at these position time graphs, that the slope tells us something about how they're moving. And more importantly, what the slope is telling us is speed. The greater the positive slope, like 1 here, the faster it's going. If I had that same one going, this kind of way, something like that, if we have, this is person number 3 up here, in that same amount of time, this person went twice as far in that same amount of time. So again, the slope has to do with the speed. If your slope is 0, your speed is 0. If your slope is increasingly positive, then your speed is increasingly large as you're kind of moving through these different things. So why is it that this happens? Okay, so I know you guys remember this from way back when in math class. Yay, math. But you guys know, get that out of the way, there we go. You guys know that when we talk about the slope of a line, a slope of something, we use that simple formula, rise over run. Okay, so it's rise over run. How far up is it going for how far over is it going? You may or may not remember this particular version of it. I'm just kind of showing it a couple of different ways. Rise over run is also known as the change in y over the change in x. So if you're not used to this notation, that triangle there means the change in y. How big a distance did it go this way versus how big a distance did it go this way? So delta, that triangle shape, means change in. So the change in y over the change in x, also known as rise over run. So in a position time graph, there's a particular meaning to that. Position here is also known as distance or displacement. They're pretty similar in terms of what they're going to do. But we're going to do distance right here. And then this one is time. So this is in meters. And then this one is time over here. So if we take a look at our graph, when we take a look at the slope of our line, slope is rise over run. So in this case, slope is equal to distance over time. Distance divided by time is known as speed. This is the connection, that mathematical connection. You guys have seen that before. Miles per hour, right? Meters per second. Whenever we see this particular arrangement of distance divided by time, we can be talking about the slope of a particular graph. So I'll kind of remind you that when we take a look at something like this, when we do divided by, remember we kind of call this the per line. So it's distance per time, or you could do meters per second. If you're including the units in there, again, that means divided by. This also means rise over run. So meters has to be on the y-axis, and time has to be, seconds, has to be on the run axis. So again, all of these things are directly related to one another in terms of how we do that. So you see this equation right here is the equation for velocity or speed, basically, is what we're trying to do. Velocity and speed are very similar ideas. I'll talk about those here in just a second, but very similar ideas. They are a little bit different. So, but velocity is the change in distance over the change in time. How far did it go and how long did it take to do that? So velocity is distance divided by time, also known as slope, which is kind of cool, actually, that they're part of the same thing here. Get my other pen back here. There we go. So this velocity. Okay, again, the slope of a position time graph is velocity. I wanted to point this out to you because there's some slightly different notation that sometimes gets used here in physics. And if you're not used to this, it can kind of really throw students off. One of the ways this, the triangle notation, I know that you guys are probably fairly familiar with that idea of this being the delta y, delta x. But I think they use a slightly different notation in math class. So like in math class, they would write it this way: y2 minus y1 divided by x2 minus x1. That would be the same thing as saying delta y over delta x. And that makes a lot of sense in math class. It certainly does. In physics, they use a slightly different notation. And so I just kind of want to warn you about this. We would say that the two, right, the y1, y1 is where it's starting. It's an initial position or its initial time. And then y2 would be its ending time or its final time. So rather than using ones and twos, in physics, we tend to use i's and f's, ti and tf. So TI versus TF, initial time and final time. Same thing, DI and DF are more commonly used, initial distance or displacement and final distance or displacement. We don't typically do the D1, D2 kind of thing. It has a slightly different meaning in physics. So I just kind of wanted to warn you about that. That definitely does look a little bit different in physics. So as we use these particular equations, we a lot of times see them presented in some kind of funky different ways. So if we have delta D over delta T, the change in distance over the change in time equals velocity. And I'm put this is a vector, so it's got a little vector arrow over the top of it. There's a bunch of different ways we can write this. So a lot of times it's written like this: df minus di equals delta t. Is a very common way to write that. Just like we would write y2 minus y1, it's always the final distance minus the initial distance. We want to know how far it went. So if it ended up, if it started at the 5 meter mark and ended at the 23 meter mark, we would do 23 minus 5 to get us our change in distance, our change in displacement. And again, delta t is a lot of times written like that. So if you take a look at this equation, this algebra on here, we get some really weird looking versions, the way that this gets represented, that can really throw students off. So velocity is distance divided by time. I can write this a couple of different ways. Velocity times delta t equals delta d is a really common way to write that as well. Distance equals velocity times time. They can also write it with this format in here, and this is where it starts to get a little bit weird, is that we'll start to see v delta t equals df minus di. And again, these are all the same. So I just want to point this out to you, that some of the reason why you need to have some decent math skills in here is to not get thrown off by the different kinds of notation that means the same thing. All of this just means slope. That's all it really means. How steep is the rise over run? That's all it means. But all of a sudden you start writing it like this, and it starts to look very different than this. So that's why I just wanted to kind of mention that when we're talking about velocities and when we're calculating velocities, don't get necessarily too freaked out about the notation and the way that they write the way that they write it. It's all related to the same stuff. Last thing I want to mention here is about checking units. Okay, velocity is distance divided by time, right? Velocity is distance divided by time. Distance has units. Time has units. Velocity also has units, and they're directly related to one another. So if our distance is miles and my time is hours, that means my velocity is going to be in the units of miles per hour. If my distance is in something else, meters, and my time is in minutes, I can get meters per minute. You need to look at the units that you are using to make sure that they match, so that you, when you are doing some algebraic rearrangements in here, you've got to be a little bit careful about your units that you're using. So here's what I mean. If you have something that's a velocity of 5 meters per minute, and it's going for 25 seconds, you can't just say times 25 seconds, because our units here don't match. They don't cancel out. You need to make sure that when you're setting up your problems that your units are consistent, that if this is in meters per minute, then your time needs to be in minutes. Or you need to turn your speed into meters per second so that the seconds cancel out. So just be really aware as you're working on these things that there's some notation differences, and to be starting to, again, dimensional analysis, be really looking to make sure that your units are consistent across the different pieces that you're using: distance, time, and velocity. Okay, mention this one kind of quickly. We've talked about this this kind of a graph before. Here's a position time graph. What does this mean? Velocity versus speed. These two words have a very similar meaning, and I do want to mention kind of the difference between them. Velocity is a vector. Velocity is a vector. Vectors have both magnitude and direction. So you could say something like 10 meters per second, but you'd have to say which way. You would either say positive 10 meters per second if you just want to do positive, negative, or maybe you'd say 10 meters per second to the north. Those both work. Speed is just simply the number. Speed is actually the magnitude of a velocity vector. They're really, really similar to each other. Like I said, in common everyday English, we use these two words almost interchangeably, and they're very similar. In physics, though, velocity is more important to us. So when I say two cars hit at 10 miles an hour, how bad is the accident? Well, it depends on what their velocities were, not necessarily their speed. I said they were 10 miles an hour, but if we're talking about 10 miles an hour and they have opposite velocities, that's a big crash. If they're 10 miles an hour with basically the same velocities, they'll never hit. Or if they do, 10 miles an hour like this way, right? Where one's coming this way and one's coming this way, that's a different, like a T-bone hit. There's the velocities are different, even if the speeds are the same. So we got to be a little bit careful with that. Just kind of keep that in mind that when we're talking about these two things, that is a part of that. So if we've got a position time graph like this, again, the slope is equal to velocity. Slope equals velocity. This one right here has a positive velocity. This one right here has 0 for a velocity. It's not going anywhere, right? It's staying at 60 meters for, I don't know how many seconds that is, 5 seconds. Then right here, what is it doing? Well, here it's got a negative velocity. Now, what does that particular mean? It means that it's going the other direction. If this is the north direction, if the position is going from, that way, and then the other position is going that way from some sort of a starting line, that's all that means. This could be a stop sign, right? It could be an intersection. I'm going one direction from the intersection. I'm going the other direction from the intersection. So the velocities doesn't mean that it's necessarily driving in reverse. It's just driving the other way. Is it going, 10 meters per second that way, or is it going 10 meters per second that way? That's all that means. If we take a look at our slopes, we can tell that this one is a little bit faster, I think, than this one is. So what is this one doing? This one is going, where is it going here? Here is from 20, right here, 20 seconds to 30 seconds. So that's 10 seconds, right? So that is 10 seconds. What's its displacement? Okay. Well, its displacement is it's going from 40 to 0. So it's going from 0 like that, df, di. That's kind of weird to say that. So it's literally going negative 40 meters in 10 seconds. So its velocity there is negative 4 meters per second. Now, what does that mean? Does it mean it's driving in reverse? No, it just means it's going in the negative direction. It's going from plus towards the 0 line, whatever that is, your starting line, whatever that is. And it keeps going at the same speed, kind of past it the other way. So again, imagine if we had a race or something along those lines where I'm looking straight down at my race and I could have someone running, if I can't run, but like that direction, there's little feet right there. There's little feet there. His head. He's going this way, right? Let's say this is our start line. If he's running this direction, if this is our start line, typically this direction is considered to be positive, right? I'm going from 0 to +5 to +10 to +20. If I'm running to the start line, that means I maybe started at -20 and then I went to -10 and then I went to the 0 spot, right? I'm running to the start and then I'm running past the start. So again, that negative direction, negative position doesn't mean he's going backwards. It means he's approaching some arbitrary 0 line from the negative direction. That's all that means, from the left as opposed to from the right. So anyway, so then it goes to the 0 position, goes through the 0 position into the negative direction, wherever that is, left or right, whatever. And then it comes back up to the positive. So it kind of changes its direction. So here's a negative velocity and here's a positive velocity again. So again, velocity versus speed. You're taking a look at what is the actual value. Is it going 4 meters per second? Is it going in the positive direction or is it going in the negative direction? Okay, last bit, I just wanted to mention this very briefly on there. There was one of these in one of the earlier position time graphs. We're typically going to talk about linear position time graphs. And I want to mention this, what happens when it's curving like this? Okay, again, what this means now is it's not covering a consistent distance in every time interval. The amount of distance that it's covering is changing. So in 0.1 second here, it's going that far and that's it. But in 0.2 seconds, it's going now this far. It's much bigger. It's a bigger amount of speed. It's a bigger amount of speed. It's a bigger amount of speed. If I did this as a particle drawing, it would kind of look like this, where the dots would be getting ever further apart, right? That means it's accelerating. That's all that means. It's changing its velocity. Its velocity isn't just a straight line. That's a constant positive velocity. This is an increasing positive velocity. That means it's accelerating. It's changing its speed. That's all it means. It's not just going +5 meters per every time interval. It's going +5 meters, and then it's going +10 meters, and then it's going +20 meters. It's going faster every single time. So with this, all that means when it curves, if you've got a curve like that, that's acceleration as opposed to constant velocity. That's what that particular thing indicates if you see that. So don't stress about that. And that's just, it's not something that we're going to deal with a bunch in this part of what we're doing in this particular chapter. But I did want to point that out, that that's what that means, is that you've got a changing velocity as opposed to a constant velocity. Now, there's something else that we can get from this, and this is the difference between the concepts of average velocity and instantaneous velocity. So if you've taken any time with slope before, you guys know that if we did the slope of this, we would kind of draw some sort of like a straight line, right? But this thing has different slopes at different spots on this curve. You guys have heard of this in math class called a tangent line. So like our slope of our curve here is pretty flat. And our slope of our curve here is kind of like that. And our slope of our curve here is a little bit steeper and steeper and steeper yet, and maybe steeper yet. So our slope is changing at every one of those particular spots. This is called instantaneous velocity. What is that slope at that particular instant in that curve? Because it's changing every moment. So what is it right there? That's what we would call instantaneous velocity. As opposed to average velocity is literally average for the whole distance. Average velocity is df minus di over time, regardless of whether it's changing or not. Average velocity is for this whole thing. So we're talking about it went from here to here. It went from 0 to, looks like 120. df is 120. di was 0. And the amount of time that it went was 0.50 seconds. That's it. This would be cm. So again, regardless of what it's doing in between there, we're just looking at how far did it go in the entire journey. We're talking about average velocity. How far did it go? How long did it take to get there? It's kind of like going on a road trip, right? If I go 120 miles and it takes me 4 hours to get there, it doesn't mean I went the same speed the entire time. Sometimes you go faster, sometimes you slower, maybe you stop in the middle and you have a picnic. But your average velocity means I went 120 miles in 4 hours, 30 miles an hour. Not that fast, right? Had a picnic, who knows? It doesn't mean I ever went that speed, but over the entire journey, the average 120 miles in 4 hours. My instantaneous velocity at any point could have been 55 miles an hour. Could have been 0 if I'm at the snack. Could have been going 80. I would never speed. Or it could have been 10 miles an hour as I'm crawling up to a stop sign. So again, your average is the whole journey, start to finish. instantaneous is at any particular instant along the line. So there you go. Just a couple of topics on looking at velocities and calculating velocities, looking at our equation. Sorry, there should be a delta there. Our equation for calculating velocity. We're usually talking about average velocity. I wanted you to get that idea of slope. The steepness of the line gives you that idea of what velocity is. And that if that slope is changing, that tells you that your velocity is changing. It's accelerating. So there you go. And I think that's it. See you next time.